So here we will try to extend the meaning of tangent line that we know already for units for a circle. We know that it is a line that intersects a circle on a unique point. So what would be such a line for a curve at particular x where the function is defined? Because any line, for example the parabola, we know that any line passing through x will cross elsewhere the curve, okay, unless only for maybe 0 where there will be only one point, one line, an horizontal line. Okay, so let's try to find out a way to extend the meaning of a tangent line. Why is it important? Because if you look at the circle, the unit circle, the line, the tangent line is very close to the circle when we are close to the considered point. So this is the purpose. Okay, so we will consider the parabola y equals x2 and the point we are considering the point 1, 1. Okay, so an idea is so if P is 1, 1, coordinate 1, 1, so if I consider points Q on the parabola that are close to P, I could always join the 2 points by a line, a second line that has this slope. Okay, so the idea, if I make these Q points, if I choose them close to P, I may find something. Okay, I will look for the second lines, how they behave, and see what I can do. Okay, so let's do that. Here is F, is recognized. Now I will consider the slope that join x, the point with coordinate 2 and the point with the x equal 1. Okay, so here is the first with slope, another slope 1.5 and 1. KQ here has an x equal 1 over 2, 1.2. Okay, here the x of q is 1.02, same close to 1. Here I'm taking points from the left of 1, so the q has x equals 0. Okay. Okay. The left, so I put L left. Okay, then 0, 5, increase the x, then 0, 8, and finally 0, 8, 8. So I took finally, yes, 4 points from the left and 4 from the right. Okay, now let's graph the lines with the slope, the second lines. Okay, passing through PQ for the different values of Q. Okay, so here it is. I considered the parabola. So we will see what we did here. Okay, here it is. So I grouped it. So I graphed 4 graphs here. Yes. So I'm considering here the point to the left, 0, 5, you see. Oh, is it for the left? No. Here is 1, 1, the other q is here. X equal to 1.5 q, then closer to 1, and the fourth one. Then let's look at the lines now from the other side. I think I did them here. No, I regrouped just these lines, this one side, okay? And now what I did here, I group it. Okay, what is weight times, sorry, what is that? Okay, we graph it this once. Okay, now what is this? Yes, again. So I think I am changing just something here, maybe the interval, now 02, 02, the interval I kept it the same, now just the lines, yes, the lines I took, okay, there were 8 in total. Now let's consider the point Q with axis X, then approach X to 1 and see if this slope of the second line has a limit or not. Okay, so let's do it. M, now the limit of M is 2. It has a limit. Now if it has a limit, let's take this slope and consider the the line that has this slope and passing by P, okay, by the point P. So here is the equation, and let's sketch this line and compare it with the other lines. Is it better line that approaches the curve or not? So here is what is happening. Maybe we don't see the line in dark, okay, is the line we found with the slope 2. Okay, now let's visualize the. Now I am graphing the parabola with the only the tangent. I'm restricting the domain from 0.5 to 1.5 to see how it is, okay? Then the second time I approached more, I reduced the domain more, 0.08. Look, it's very close to the parabola. And the last one, 0.9 to 1.1, and this also is very close. See? You see how it is very close to the graph of the function. This is why we are interested on these tangent lines, because our graph will be will behave almost as its tangent at close to the considered point. So that's this gives the motivation to set this definition for an x0 in the domain of f. We will call the tangent line to the graph of f at the point x0 f x0 the line that has this equation y minus fx0. It passes to x0 fx0. It has the slope m, with m given by this limit, okay, when it exists. And also we will call this number, this limit, when it exists, the derivative of f at x0. Okay, so for our example of the parabola and with x0 equal 1, the f prime 1, the derivative of f at 1, is the limit of the variation, which we can write like that. So it's just computing a limit of a function. Here we have an indeterminate form. We need to remove the indetermination. So we factor the numerator, simplify, and get the number 2, the slope 2. Okay, so the derivative is 2. So to summarize, so the purpose here was to find an explanation or an intuitive explanation to justify the definition of a tangent line to a curve at the point, and to introduce for the first time the quantity derivative of function at the point, which is nothing than a slope of the tangent line to the curve. And we learned also that how we did the equation of the tangent line, how we can find it, what is its equation, what is its slope. Okay, so this is what we want to